All right. So I'm going to ask you guys the same question that I asked my CISP360 class. Are there any questions? Do you guys have any questions about the topics that we have talked about so far? The homework assignment? Okay. Any questions about the homework assignment? Yep.
There are multiple possibilities for.
There are some don't care, signals where, you just have to put an X or question mark to basically indicate, it doesn't matter what those things are, it will still work. So you have you have flexibility there. But there are certain signals that have to be a 1 or they have to be a 0 or they have to be a certain value, but there are multiple bits to the same pin. So that you have to kind of decide. Okay? So in general, you would much rather be more specific than less specific. In other words, if you're not really quite sure whether something is not care or it has to be a 0, because the default is kind of 0 for most signals, then you write down a 0. Okay? On the other hand, if you know for sure this is not going to impact what you're doing whatsoever, then you can just put a not care, put an X, in that box. Okay? Any other questions? No other questions? All right. So if there are no other questions, we are continuing with our topic.
Are you recording?
I believe so. Let me just log in first, and then we'll check the recorder. Yep, it is recording. All right. So this is 360. Let's give it a 360. All right, so this is where we are, with non-integer representation, and this is, there's some discussion of fixed point representation. Fixed point is really kind of easy because what it is there's an implied binary point in a number representation. So if you have a 12-bit number, you can put an implied binary point anywhere along the way. It's just that you will have to keep track of the binary point. When you do multiplication, you have to remember to shift the binary point of the product. And when you do division, you have to remember where the binary point is supposed to be when you do division. Okay? So I'll give you one example. The example is going to be on mouse pad, just so that it is going to be captured. All right, so here's mouse pad. So you basically look at all the bits. Okay, so we'll go take a look at a particular bit, 8-bit number. Okay, this is just an 8-bit number. Okay, which normally, if you look at this as an unsigned number, this normally would represent 128 plus 32 plus 16. Excuse me, plus 16 plus 7. Okay, which is a particular value. So the way you do fixed point calculation is instead of looking at the value represented by this bit pattern as an integer, you just basically say, oh, there's an implied binary point here. But that binary point can be anywhere. You get to decide where that binary point is. Because when you look at the bit pattern, you have to take care of the actual value, okay, how to interpret the value of the bit pattern. So there's no actual binary point in the number itself. It is all assumption of your program. Are there any questions about this? Yep.
Is there a particular place that would be more advantageous
Nope.
to us?
It all depends on your application. Because if your application has to deal with only, like from 0 up to just a little bit less than 1, then your binary point will be all the way to the left-hand side, right? Because those are the values that you need to represent. For instance, if your application needs to deal with SAE units for branches and sockets, then they're all less than 1. Well, I know they are big, huge, sockets and whatnot, but normally we only use, less than 1-inch sockets. So in that case, you put a binary point all the way to the left-hand side, so you can represent all those fractional values that you need to represent. But the number itself, if you go to GDB and you look at the memory location, it's nothing more than just an 8-bit number. It is how your program interprets the 8-bit number that is important. Okay. Are there any questions about this? The most important part about fixed point calculation is you have to remember you have the number itself. Okay, so let's say the n is the number. Okay, n is the integer value of the bit pattern. And then you have a multiplier. Okay, so we'll call E is the magnitude multiplier. Okay, which is usually 2 to the power of some exponent. So we'll call that. I picked E already, so maybe we should change. We'll pick that one as E, and then the exponent is X. Okay, so the value represented by the bit pattern now becomes n, which is just a binary bit pattern, but the other part is implied. This part is implied, and the assumption is entirely up to your program to decide. This is not floating point number, and that's why the exponent is not explicitly represented. It is just implied. Are there any questions about this part? Now, fixed point numbers have applications. Okay, if you look at the flexibility of a fixed point number, is it flexible?
No.
No, absolutely not, right? Because the binary point is fixed, okay, and that's why it's called the fixed point number. But in terms of calculation, efficiency of calculation, do you think fixed point numbers are more efficient, or do you think floating point numbers are more efficient when it comes down to how much time it takes to do addition, subtraction, multiplication, and division, and how much silicon is needed if you want to implement those calculations in hardware? Which one do you think is more efficient? Fixed point calculation are by far, okay, more efficient. So that's why people still use fixed point calculation whenever it is possible. Okay. It may not apply today because we do have cheap processors now, but in the past, okay, with MP3 decoding, MP3 decoding is actually very, very friendly to fixed point calculation. So all of the calculations to decode an MP3 stream can be done using fixed point calculation, which means if you want to make a portable device to play MP3 music, you don't really need to pack a lot of processing power in it. Is that okay? Now, the flip side is Auto-Enrolment, okay, which is another encoding scheme. That one, until at least recently, it's all floating point calculation. And that's why people cannot make cheap, inexpensive Auto-Enrolment decoders, because it just takes more hardware to implement. Okay, so I'll just go ahead and point out those terms, because for some of you understanding what it applies to make it easier to remember and understand. So MP3, I don't think we need to. So I'm just going to go to MP3 decoding, and the first page is going to be the one that actually applies. Okay, so if you look up here, it doesn't have fixed point calculation here, but this one is efficient. Okay, so if you read through how it is done, it is actually quite efficient. And the other one is called OGG Vorbis, VORBIS. And it is a different encoding scheme, and that one is not popular, even though it's open source. This one is not copyrighted or patented, unlike the other one. It is not as popular because of the requirement in hardware. Okay, it cannot be done with less hardware compared to MP3. Is that part okay? All right. So that's the extent we'll talk about in terms of fixed point calculation, because it's not it's kind of specialized. Okay, a lot of programs do not use fixed point calculation because it's not you have to take care of everything. Okay, you have to implement your own multiplication, you have to implement your own division. Addition and subtraction are easy. Okay, because when you subtract or add two numbers and they have the same fixed point, then addition will just work by itself. Subtraction will still work by itself. Comparison will still work all by itself. But multiplication requires the shifting at the end, and then division also requires special attention. Any questions about fixed point calculation? No questions? All right. So we just talked about fixed point calculation. The limitations, it's really just the range of numbers that you can represent is fixed. Okay, just like integers. except you're changing which portion of the real number you can represent, but nonetheless it is limited. Do you guys want one more example of a floating point conversion by hand?
Sure.
Okay, all right, so let's do one more conversion, and then we'll move on to non-number representation, which is actually a lot easier than what it seems. Okay, so we'll go back to here, and then we'll take a look at one more number. Basically, if you want to have a clean number so it doesn't end up with a lot of gibberish, zeros and ones, what you are looking for, okay, let me switch back to mousepad here, is something that looks just like this, okay? Because if n is a very easy number to represent in binary, okay, let's say it can be any integer. The key is you have to have this number as n times some exponent of 2. Doesn't have to be a positive exponent, doesn't have to be 1, 2, 4, 6, 8, and so on. Can be negative, can be fractions, okay, involving a power of 2. So it can be a fourth, can be an eighth, can be a 16th, a 32nd, and so on and so forth. But the key is E has to be a power of 2. So if a number can be represented that way, the binary representation in floating point representation is going to be quite clean. You just end up with a bunch of zeros in the fraction. Okay, so I'll let you guys decide what you want to do for this particular number. Pick one.
12.
Okay, 12. Okay, so we'll look at 12. So when we look at 12 normally, it has an implied magnitude of 1. Does that make any sense? Okay, because 12 is always the same as 12 times 1, which seems kind of obvious. But the next thing we'll do is to look at 12 as a binary number. As a binary number, 12 is 1100, right? And 1 as a power of 2 is 2 to the power of 0. Is that okay? Is everybody okay with this conversion here? What about the next step? The next step is we have a binary point that is implicitly here, right? Does that make sense? Okay, any integer has an implied binary point or decimal point if it's base 10 to the right-hand side of the entire number, because it just has no fractional part. So we usually do not write that point because it has no fractional part. So what we want to do is to move this point all the way to here, right? Because we want to normalize the number so it becomes 1 point and then a whole bunch of fractional parts. In doing so, every time we shift the point over to one place, we are halving the value of this part. To make up for that division by 2, we have to multiply by 2 on the other side. So that means in this case, we have to shift the binary point 3 times. 1, 2, 3 into this place. Then we have to increase this by 3. So after everything is done, it becomes 1.100 in base 2 times 2 to the power of 3. Is that making any sense? Well, let's double check, okay, because I don't trust myself. Okay, let's double check to see whether this makes sense or not. This one is just 12 times 1, which is 12. Okay, that's easy. What about this one? What is 1.1 in base 2? What is the value represented by 1.1 in base 2? We have 1, 1, and then we have 1 what after that? 1 half. Okay, so it's 1.5. Okay, so it's 1.5 in base 10. And what is 2 to the power of 3?
8.
That's 8. 1.5 times 8 is, in fact, 12. So this is how I can kind of double check. This is kind of like a sanity check, just to make sure that everything is correct up to this point. But you can see how I check it, right? Because I just do the base conversion, carry out the conversion to make sure that I still end up with the same value. So I know that I'm not shifting the point in the wrong direction, or I'm not compensating the exponent in the wrong direction. Him first, and then you go ahead.
So where did 1.5 came from again?
It's 1.1 in base 2.
Ah, okay.
Yep, go ahead.
So if you shifted the binary point all the way to the left in this example, why did you pick the third spot in your example, the 10010?
Because the standard of how a floating point number is represented is we only represent the fractional part of a normalized mantissa. Okay, this is called the mantissa. This part here is called the mantissa. This is not normalized because we have the binary point not right next to the unit or the 1. Okay, how many ones we have? This one is normalized. Okay, so according to the IEEE standard, this one point is actually implied. The actual bits that are represented are these bits. So that's why we want to normalize first, so that we know what the fractional part is supposed to be, and that becomes a part of the actual binary representation.
I meant your 8-bit number that you had originally put. Your original 8-bit number was 1001 0111.
Right.
And you moved your point 3 places to the left.
That one is just because, maybe in this particular application, 1/8 is the smallest unit I need to represent. So it's completely not related to what we are currently doing. Okay. All right. Okay, so what do we do next? Next, we have to identify the various components. What about the sign of this number? What is the sign of 12? Is it positive? Is it non-negative or negative?
Non-negative.
So the sign bit is going to be a 0. Very good. The actual exponent is 3, okay? But the bit pattern for the exponent part, or I'll just call this biased exponent, is going to be what? Does anyone remember the bias constant? What are we adding to the actual 1023? Very good. So 1023 plus 3 is 1026. Okay, this is all base 10, okay? And then the fraction part, okay, the fraction of the mantissa would be 100, oops, 11, oh, no, it's just 100 and a whole bunch of other zeros in base 2. Okay, so I'm now converting the number pretty close to the entire binary representation, but it's in different parts at this point. Okay, we have components. The first component is the sign, which is an easy one. 0 means it's non-negative, and 1 means it is negative. The biased exponent is the one that you have to remember that it is biased by 1023. So whatever the actual exponent is that you want, you have to add 1023 to it to become the value that will be represented using these 11 bits. The other, well, let's see, 52 bits. The other 52 bits will be the fraction only, which means the 1 point is already implicit. We are only representing whatever is to the right-hand side of the binary point. In this case, it's just 1 followed by all zeros. Okay. So now we are now ready to. Let's do one more step first, okay? Because we eventually have to convert 1026 into a binary representation. But this one is easy because this is 1024 plus 4. So we only have 2 powers of 2 in this number. So it'd be 1 followed by a bunch of zeros. Okay, I'm just throwing a bunch here. I will count later. The 4 is another 100. And the whole thing is supposed to have 11 digits. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow.
Shouldn't it be a 2 instead of 4?
Oh, you're right. Sorry. I was already so impressed, and then I got the wrong one. Darn it. Okay. Okay, fine. So now we have, all the binary representations of all the components, right? So the next step is to pack everything into one long string and then break it apart again into chunks of 4. Okay. So now this step here is only needed because I want to be able to see it as a hexadecimal number. Okay. If you don't need to do that, it's okay. This is already enough. Okay. So we have a 0 for the sign. We have 1. Okay. I'm not going to count too many of these zeros here. So, and then we have this bunch as the exponent, and then we have 1 followed by a whole bunch of zeros as the fraction. Okay, this is the actual 64-bit number. I know there are not enough zeros to make up for 64-bit, but you can just say, okay, there will be enough zeros to make up for 64 bits. This is the actual binary representation of a 64-bit or double precision floating point number. And it's supposed to represent the value of 12. Okay? So to test whether this is working or not, Okay, we first have to convert this into a hexadecimal number because I have to be able to punch in the binary representation into the compiler. Okay, and C and C++ does not have binary numbers. You cannot specify binary constants. So the closest thing would be a hexadecimal or octal number. So in this case, we'll arrange these in chunks of 4. So the next step is to just, I will copy and paste it. I know you cannot do it on your paper, okay? But you can just kind of capture the concept, okay? How it is done. Okay, now we break it up into chunks of 4. So copy and paste one more time. 1, 2, 3, 4, break, 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 and the rest are all zeros. Are there any questions at this point? Because these 3 lines that do not seem like I'm doing a whole lot. Okay, in one step, going from the first line to the second line, I took out all the spaces because those spaces originally were here to separate the components of a double precision floating point number. But I have to take out those spaces because I need to break it into chunks of 4 bits. So the last line is just taking a look at the 64-bit pattern and then break it up into chunks of 4. So now I'm ready to convert into hexadecimal numbers. Okay. Hexadecimal numbers are fairly easy to convert. It is just a table lookup because you just have to look up 4 bits and say, okay, what is the hexadecimal digit for those 4 bits? If you're just starting off, it might take some time to get used to it. But once you have done this like 1 or 2 semesters, it'll just be like that. It's really natural. So this is basically this is a 4, 0, 2, that's an 8, and a whole bunch of zeros. Okay. So now the question is, how many zeros are we talking about? Well, at this point we have 4 hexadecimal digits already taken care of. 4 times 4 is 16. So out of a 64-bit number, we have 16 bits already specified. So we have 64 minus 16, which is 48 bits left. And those are all zeros, and they are all least significant digits. So the quickest way to specify 48 least significant digits is to use the left shift operator. So we just say, oh, give me 48 zeros on the right-hand side as the least significant digits. So that's how we can specify this number using 0x4028 because it's a hexadecimal number, left shift 48, and of course we have to do the typecasting because if you just specify 0x4028, it is a 32-bit number, and as a 32-bit number, if you left shift it 48 times, you end up with 0. So you have to cast it into a 64-bit number first so that the left shift will know, oh, we're not going to shift anything out, at bit 31. The number is actually much longer than that, much wider than that. Okay. So now we can go to a DOS prompt or command line interface. Oh, maybe pick another one here. There we go. So now we can write this program, okay, which we already have a few. So we'll take a look and see. No, I think last time I put it into the temp folder. I'll do the same thing here. So we'll do another program. I'll just call it d.c. First of all, we'll include stdint.h, which is not 100% necessary because I know if I specify unsigned long, it will give me a 64-bit number. But that's specific to this platform, okay? But if you include this particular header file and you say uint64_t, it guarantees that you end up with a 64-bit unsigned integer regardless of the platform that you're on. So that's why it will allow you to write much more portable code. So the same code can now run on a 16-bit platform, a 32-bit platform, or a 64-bit platform. Okay. uint64_t, and we'll just call it x, and x is now uint64_t because we have to cast the constant before shifting. So it's 4084. Oh, what was it again? 4028. Okay, thank you. 4028, and we'll shift it 48 times, and And that's my entire program, because I'm going to put a breakpoint on the line of the return, and just use the casting trick to look at the number as a double precision floating point number, and see that it is in fact representing the value 12. So GCC, I'm going to shortcut here because it only has one single source file, so I'll specify the executable on the same line. Put a breakpoint on line 8, run the program, and if you print x all by itself, it is an integer. In fact, it's a huge integer. Okay, if you print it in hexadecimal, you should see the number that we were talking about, 4028 followed by 12 zeros. But these are all in hexadecimal. On the other hand, if you want to look at it as a binary number, because you need to chop it into tiny little pieces, it becomes, /t will give you the binary number. Okay. GDB actually does allow you to specify something like this and print it as 12. Okay, but that's an internal conversion. Okay, so the trick to do this without using the internal conversion is to do the pointer trick. Okay, so we are going to say something like that. Okay, I explained this already, so this is the last time I'm going to explain this. Darth Vader's voice. This is the last time I will explain this. The Emperor is not pleased. Nah, you guys. Some of you are way too young to remember Darth Vader, and the new movie does not have Darth Vader either, right? All right. So we start with x, and then we take the address of x. But x is a 64-bit unsigned integer, and the address of that is an address of a 64-bit unsigned integer. But that's okay because the typecast operator is applied to the address. In other words, I'm telling the compiler, hey compiler, I know what I'm doing. Treat this address as the address of a 64-bit double precision floating point number. Now, if I explicitly cast something, the compiler does not question it, because after all, C and C++ were invented by really experienced programmers for really experienced programmers, okay? Which you are assumed to be, right? So, by the end of the typecast operator, what do I have? I have an address of a double precision floating point number. And with an address, one thing you can do to an address is to dereference it, right? So you're basically saying, oh, give me the value at that address, okay? But what kind of address, what kind of value are we talking about? How should I interpret those individual bits? Oh, those 64 bits is a double precision floating point number, and print it as such. That's basically what this print command is going to do. So that's why, this is validation that we are in fact dealing with a value of 12, but represented as a double precision floating point number. Are there any questions about any of those statements that I just made? Other than, could you say that again? Because I cannot remember what I just said. I can remember the concepts that I just talked about, but the exact sentence I cannot remember. Is that part okay? No problem with this? Yep, go ahead.
Isn't it supposed to, that one in the beginning, isn't it supposed to be a leading zero because of the positive number?
That is correct. It does not print leading zeros, unfortunately.
Okay.
I do not know whether it can print leading zeros, so let me see. Okay, so occasionally I have questions, right? So how do I find the answer? Well, first thing is help, okay? And I know help print is not going to help me a whole lot because I have read this many times. Because when it comes to the format, it says, see the X command, okay? Which is fairly typical, because it doesn't want to repeat everything that is already mentioned in the help page of X. So I would say help X, which is a command that we will use a lot later on in this semester. So we look at this and go, okay, we can use T for binary, but it doesn't have a way to specify the number of digits. Okay, FMT is a repeat count, okay, followed by a format letter and a size letter. We're dealing with a format letter here, okay? The format letters are octal, hex, decimal, unsigned decimal, binary, float, address, instruction, char, string, and Z. And this one does have 0 padded, but it's only in hexadecimal. So when you print it as a binary number, there's no option to pad zeros or pad zeros to the left. or at least that's what it implies.
Okay.
Okay, but that's a good question. It's a fully legitimate question. But the answer is no. GDB does not natively have the ability to do that. Okay. Okay. Now the other question, or the other thing that you can do about a program like this, is to go in here and you can say, but tech, I think that's also smoke and mirror. Okay, because after all, it is dependent on GDB to do it. So what you can do is to actually declare a variable called double, and here you basically say d equals to, and then the same thing that we talked about earlier, uint64, double %x. Same thing that we used in GDB, but this time it is a part of the C program. And then if you don't want to use GDB at all, you can do the proper pound includes, and then either use cout or printf to print the value of d, and that will confirm that we are actually doing the conversion correctly. Okay. Are there any questions about what we just did? No questions? All right. Well, let me test and see if you can come up with the smallest value, the smallest actual value, absolute value that you can specify using the 64-bit or double precision floating point number. What is the smallest value? I know you can look it up on Wiki, but just using your understanding of the material, what do you think is the smallest value that can be represented? And this is, by the way, kind of a trick question. Okay.
Greater than 0? Greater than 0?
Greater, not non-zero. Yeah, the smallest non-zero value that you can represent. Okay, so this is the way you look at it. The Mantissa is a 1 point, and then you have the fractional bits, right? Okay, so the 64 bits simply means there are more bits allocated to the fractional part, times 2 to the power of the exponent. But you have to remember the actual number represented is biased by 1023, so the power that you want to raise to is actually whatever is represented as the binary number, but you have to remember the minus or subtract 1023 from it. Okay? So now the question is, given this is how we utilize the binary digits in a 64-bit floating point number, what is the smallest value? How do you specify the smallest possible value in this case? The answer is, yep.
1 on the very right.
Well, the obvious answer is to specify all zeros, right? So it becomes 1.0 blah, 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 all zeros, times 2 to the power of negative 1023. That would be the smallest possible value that you can represent. Is that making any sense? But if that is the smallest value you can represent using all zeros already, how do you represent 0? The sign bit is independent, right? The sign bit is all the way over here, saying, oh, this number is non-negative, and that's why we have a 0 for the sign bit. But the sign bit does not specify the magnitude. It doesn't specify the value at all. It just says, is it positive or non-positive, negative or non-negative. So how do you represent 0? The problem with representing 0 is this implied 1 point here. Okay. In other words, if you only look at how this number is formatted, there's no way to represent 0. Yep.
What if you were to assign that number and then subtract it from itself?
Then it cannot be represented. The value 0 cannot be represented, at least not right now. Okay? And the reason why it cannot be represented has to do with the implied 1 point in the representation of the number. It is always there. You cannot get rid of this 1 point. So as it turns out, the IEEE decided that if you specify all zeros, it actually means the value of 0. It does not mean 1 times 2 to the power of negative 1023, which would normally be how it is interpreted. But because we do need to represent the value of 0, it makes an exception and just say, if all of these things are zeros, it means actually 0. It's an exception to how we normally interpret the bits. So for those of you who think, well, I'm not really sure about that, double precision floating point number, and where did I open that page? Oh, as a new page. Nope, it's already here, so certainly don't want to close it. Okay, so if you look it up, it says endianness. Okay, that's not. Eventually, we will have to deal with endianness, but at this point, we don't. Okay, let me see if I can just find 0. Okay. And by the way, it does have all the examples, a whole bunch of examples. Okay, execution speed. Okay, I think it's in the general page of floating point numbers. So if I look for zeros over here, I can't read it when it's like that. I'll zoom out first, and then I'll zoom back in when I get this part. Okay, it's probably earlier. Presentation, there we go.
There was a section about exception handling.
It's not exception handling, it is an exception to the representation. Maybe special values. Let's look for special. Okay, there we go. It has special not a number of values, the nans, the infinity, the assigned zeros. There we go. Subnormal numbers. No, those are all general discussions. Well, suppose we can go there. That's just a overview. Well, instead of spending any more time to find it, okay, I can just tell you that if all the bits are zeros, it is no longer representing a non-zero value. Instead, it is actually 0. Okay? Is that okay? You guys buy it? Okay. What about the largest possible value, just using this interpretation? How do you specify the largest possible value?
All ones.
Yep, all ones. Yep, except for the sign, because that just controls which direction. But if you specify all ones, then the value represented by that becomes 1.1111, all ones here, and then you have 2 to the power of 11 ones minus 1023. 11 ones would be 2047. Minus 1023 will get you 1024. So basically, about 2 times 2 to the power of 1024, which is very close to 2 to the power of 1025, is the largest number you can represent. But that's actually interpreted as infinity, as positive infinity. So it's not really a number that we can represent. Yep.
But I was wondering, so do we always have to subtract 1023?
That is how you interpret the bit pattern. But the bias is there. The bias is a constant of 1023.
And it's always a negative 1023.
It's biased by 1023, which means if the actual exponent that you want is 0, then you specify 1023 as an unsigned number in the binary representation. Yep. Yep, go ahead.
So if 0 is at the low end and infinity is at the high end, not a number like division by 0, and I'm guessing the square root of 1.
I think the NANDs are, they're special. Well, let's take a look at this one. So there are quiet NANDs and not so quiet NANDs. Squeaky NANDs. I'm just looking at the representation here. Okay, encoding, that's what we want. Okay, the IEEE 754 standard conforming floating point storage format. In that format, NANDs are identified by specific predefined bit patterns unique to NANDs. The sign bit does not matter. Binary format NANDs are represented with the exponent fields filled with filled with ones, and some non-zero numbers in the significand, which is the fractional part, to make them distinct from infinity values. So infinity would be all ones, okay? And there's positive infinity and there's negative infinity. If you have all ones in the exponent and at least 1 0 in the fractional part, then it becomes a NAND, becomes not a number representation. And then there are different implementations. Most processors set the signaled quiet bit to non-zero if the NAND is quiet. So, okay, let me just kind of backtrack a little bit here. What is quiet and what is not quiet? When the calculation ends up with a NAND, not a number, depending on how you want to deal with it, it can raise an exception. In other words, the processor can basically say, hey, this is something I cannot handle. Operating system, hey, tell me how to deal with this, okay? Or this is not quiet, okay? If anything that requires the processor or the operating system to deal with is not quiet. Or the other one is it can just quietly and say, oh, this is not a number, and put a NAND representation as a result. So that's the difference between a quiet and a signaled NAND. But that's the, basically these are all the representations. So one thing we can do is to test this, right? So we'll go ahead and specify infinity and then see how GDB is going to print it out. Right? Let's do that. How do I specify that number easily? We have all ones except for the sign bit. Right? Because we want all ones for the exponent, and then we want all ones for the is my caps lock on? Yep, it is. That's why. Okay, so how do we specify a 64-bit number that is basically all ones except for the most significant bit?
Overflow it and then shift.
Okay.
0 minus something minus 1.
Okay, well, let's see. It's a 64-bit number, okay? We can specify, 8 F, 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 F. That would do it. No, that won't do it. It has to be 7, right? Because the 8 is the bit that I want to turn into a 0. So if I specify this number, it is basically 63 ones as the least significant part and a 0 as the most significant part. Is that okay? But that's a really awful way to do it because I have to count the number of F's, okay? And I usually get it wrong. So one way to do this without doing this is to specify where the 1 is supposed to be, okay? So the 1 is easy because it is supposed to be bit 63, okay? So, but this is only specifying, this is flipped from what I want because this will only specify a 1 where the 0 is supposed to be, and then everything else is 0. Yep.
What if you shift it to the 64 and then subtract that?
If you shift by 64, then you end up with 0. Because the number only has 64 bits. If you shift in 64 zeros, it becomes all zeros. So you
shift by 63 and then subtract.
You don't need to subtract. You can do this instead. You can do this. Bitwise not. Okay. Does everybody understand this code here? The code where how I set x. Okay, I put a 1 where the 1 is supposed to be. The rest I use shift to shift into, and then I take a bitwise NOT so that the 1 turns into a 0, and all the zeros, all 63 zeros turn into 1s. Okay, all right. So now we want to take a look at this program and see what happens when we run it, and we will do it in GDB too. Okay, so gcc-od-g over here, and d.c, gdb d. We'll put a breakpoint on line 10. Well, we'll put a breakpoint on line 9 first. Okay, run the program, and we print out x, and x is all zeros. I did something wrong. I know why.
Is it bitwise not the priority?
Yes, it has to do with priority. Okay. While in doubt, put in extra parentheses. Then it cannot be wrong. Okay. GDB is to put the breakpoint on line 9 again. Run the program. Print x. That looks about right to me. How do I know it's about right? 1, it is a huge number. 2, is a prime number. It's an odd number. Okay. But there's an easy way to check that, because does anyone want to count?
No.
Fine. How about that? Do you want to count? But it looks about right. Okay, so now the moment of truth is, if I do the trick that I did before, okay, what is going to print? It says it's a NAND. It is not a number. Okay. If I single step and actually put this number into D and I print D, D is also interpreted as a NAND, as a not a number. But it's actually infinity. But for some reason it does not print it is infinity and just say it's not a number. Infinity itself is not a number. Okay, it really is not a number that you can process, because you cannot say what is 1 plus infinity. Well, we don't know what it is, because infinity itself is not a number. All right, so we still doing okay so far with floating point number representation. So if I give you a trick question like this, let me see if you can come up with an answer, or at least come up with an approach to do this. Okay. With small values like 12 or half or 3/4 or something like that, it's easy to process because we can clearly see it is a integer times 2 to some kind of power. Okay, because we want to eventually convert everything into this format in order to make it work. But what if you have a huge number to begin with? Okay, so I'll just give you one particular number. What if I want to represent 6.8 times 10 to the power of, let's say, 20. That's a pretty big number. So how do I convert this number into a double preceding floating point number? This is all in base 10, okay? So, but how do I do this using that process? One way to do it is to basically say, oh, this is 6, 8, followed by 20 zeros, right? Represent that in binary first, but you'll be running out of digits, okay? Okay, let's think about how many binary digits we need for something that is 10 to the power of 20, okay? How do you guesstimate? Without using your calculator, without using log or, to exponent on your calculator, how can you guesstimate how many digits you will need to represent a value that is something times 10 to the power of 20? The 6.8 I'm not too worried about, okay? Because 6.8 just requires 3 bits or so, okay? The magnitude is about 3 bits. It's the 20 that I need to process. So the trick to do this, obviously this is not really a part of the curriculum of this class, but I think it's a neat trick that most people should understand. 2 to the power of 10 is exactly 1024. Okay? 10 to the power of 3 is 1,000. Right? So we say, well, that's approximately the same. That's the trick. Because now we look at 20 and we say, oh, this is basically, okay, I'm going to go back to my mouse pad here. Okay, so let's do this. Okay, 6.8 times 10 to the power of 20 is 6.8 times 10 to the power of 20. But then it is approximately, okay, so I'm going to use this to represent approximately. So this is approximately 6.8 times 10 to the power of 2 first, okay, because I want to only deal with, like 3, 3, 3, there are 6 of those, okay. And then it times 2 to the power of 10, and how many of those do we have? In other words, once I take the 2 out of, okay, let me just use the right notation here. This is to the power of, this is to the power of, okay. So I just took 2 out of the exponent out of 20, so we have 18 left, right? Out of the 18 left, we have to divide it by 3, okay, because every 1,000 is about 1024, and every 1024 is taking care of taking care of 3 digits. So that means we have to basically say this is the exponent, okay, 10 times 6 over here. Okay, let me not skip that one step because I think some people are not getting that part. Okay. 18. Is that okay? I just broke up 10 to the power of 20 into 10 to the power of 2 times 10 to the power of 18. Is that part okay? All right. The other part I am not going to do much about, so I'm going to keep this part here. In fact, I will say this is 6,800. Okay, is that okay? No, 680. There we go. Okay, 6.8 times 10 to the power of 2 is 680. Is that okay? Yeah. All right. So we'll only have to take care of the other part. Okay, this is the trick. 10, okay, I'm not going to skip any steps here. Is that okay? All right. So the next step is to, oops, break this apart, okay, and say this is 10 to the power of 3, okay, but do this. Is that okay? All right. So now we use the approximation. So the approximation goes in here. Oops. We still have 680 here. But instead of using 1,000 to the power of 6, now we say, oh, 2 to the power of 10 is about that value. Is that part okay? This is the trick. This is where we go from powers of 10 to powers of 2. Is that part okay? All right. But once we get through this step, we can continue to use the equal symbol, okay? Because from here on, it's going to be the same thing. Okay, what is 2 to the power of 10, and then that whole thing to the power of 6? If I want to combine the exponents, we end up with 2 to the power of what? 60. 60. Very good. So the question is, can we represent this value, 680 times 2 to the power of 60, using only 64 bits? The answer is nope, cannot do that, right? Because 680 itself needs how many bits?
Great.
No. 680 is, okay, what is the smallest power of 2 that is greater than or equal to 680?
512.
Okay, you did not read the question.
Oh, sorry.
2 to the 10 is the biggest power.
1024. Okay, 1024 is the value, but it's 2 to the power of 10. 10. Okay, so that means in order to represent 6.8 times 10 to the power of 20, how many bits do I need? We know the other part, the magnitude part needs about 60 bits already, okay? But 680 itself also require 10 bits. So we need 70 bits to represent the value that we want to represent. So which also means you cannot just express the entire number first and then do the trick that we just talked about, because a 64-bit integer cannot represent the quantity that we want to represent. And this is not even close to the largest value that you can represent using double precision floating point number. Okay? So now the question is, how do you do the conversion? Because when people type in a number, they type it in base 10. But you need to represent it in base 2 as a double precision floating point number. So the question is, how do you do that conversion when the number is really big or really small? What do you think? So you start with something like this, okay? 6.8 is not really the big deal. The big deal is this part here, okay? So what do? You can parse the 20 pretty easily, okay? So you can say, okay, we know the power of 10 is 20 as a value, 20, okay? But how do you convert that into a power of 2, or to look at this number and convert it into a power of 2?
You mean convert it into power of 2 that we can represent in 64 bits?
Right, because you cannot just spell out this number, okay? Because this 20 is not even close to the largest number we can represent. What do you do when this is 40? Well, because the whole argument of, oh, we can bump up to the 128-bit integers doesn't fly when this is becoming, 40. Okay, it just you run out of digits even with a 128-bit integer. Okay, and that's not even close to the largest number of value that we can represent either. Okay, so you cannot use that approach. So what do you do?
Break it up in piecemeal?
Break it up in piecemeal. Okay, right. So what do you do when you break it up in piecemeal?
Stored in 2 locations. Or represented in one path, like one half is this and the other half is this, like some.
Well, you have to basically write some code to do it, okay? And I will leave it up to you guys to think about it, okay? But that's not going to be your homework assignment. That's because it really is much harder than what you guys really need to deal with in this class. So your homework assignment is going to have a range limit, okay? I only need you to deal with smaller numbers that can easily be done by, oh, I can express this as a 32-bit number times 2 to the power of something. Okay, so your numbers, or the range of numbers that you have to deal with, is definitely a lot narrower than the full range of a double precision floating point number. But I do want you to kind of think about this a little bit and think of an approach to do it. Okay, it's not your homework assignment, but I think it'll be helpful if you just kind of think about it. Okay. Next question: banks. Okay, Wells Fargo Bank, Bank of America, and so on. They need to deal with pretty big numbers too. So the question now is, how do they represent those numbers?
Well, they know there's only going to be 2 decimal places, right?
Sorry?
They don't factor with interest, they'll factor in very, very small percentages.
Right, exactly. I think they keep track of down to 1/10 of a cent. That's the smallest unit. Internally, they keep track of 1/10 of a cent. But when you do calculations, when you have interest, you have exponents, right? So then you have to deal with all kinds of calculations like that. So the question is, do you think banks use double precision floating point numbers to represent the quantity or the money amount that they have to deal with?
No,
Why not?
because our monetary system is a fixed number.
Okay.
So that's what they deal with.
You're right. That's exactly what they do. Now, in the past, we're not going to do it in this class. In the past, banks or mainframe computers, they use BCD to represent numbers. Now, BCD stands for
Biggest common denominator.
Is ABCD missing the A? No. They could easily have gone for ABCD, but BCD itself stands for binary coded decimal. Okay, if you add American to the first letter, then we have ABCD. But it's not, okay? It's just BCD, okay? So BCD stands for binary coded decimal, which is extremely confusing. So is it binary or is it decimal?
Yes.
Yes. Yes is the right answer, okay? So what they do is they look at a byte and they say, well, a byte has 8 bits, okay? In order to represent the digits, we only need 4, right? Because we only have 0 to 9 in decimal. So they look at each 4-bit number or each 4-bit chunk and say, we'll use one 4-bit chunk to represent one decimal digit. Okay, so let me just give you an example. So let's say we want to represent 451, okay, as a base 10 number. So what they do is they look at 4, they look at 5, look at 1, and let's say we only want to use like 16 bits to represent this number. Okay, so the 1 is 0, the 0 is 0, 0, 0, 0, the 4 is 0, 1, 0, 0, the 5 is 0, 1, 0, 1, and the 1 is 0, 0, 0, 1. That turns out to be, this part is the BCD version of 451.
So it's kind of like the way hexadecimal transfers.
Except there's no A, B, C, D, E, F represented, okay? That's binary, that coded decimal. And banks used to have mainframe computers that can only deal with BCDs. That's how they do addition, that's how they do subtraction, that's how they do multiplication and division. Because they need to represent the exact value of money in bank. They cannot afford to use floating point numbers, because back in those days, I think we only have like 16-bit or 32-bit floating point numbers, and they require more hardware to deal with those values. And binary coded decimal number was basically how they do all the calculations. That's how numbers are stored. I would not be surprised if Social Security is still using BCDs on their mainframes. Yep.
So are you saying that now they use floating point numbers?
They do not use floating point numbers.
But you said they used to use this.
They used to use this. I think these days they probably use fixed point numbers instead of BCDs. So they would use binary numbers, but the fractional part is specifically here or there or somewhere else. Okay. And all of this confusion between binary and decimal is only because of what?
Because we memorize.
No, because we chose to use base 10 because we got 10 fingers, which is a stupid number. Okay, 10 is a really stupid number from the perspective of computer science. Well, I guess 7 would be worse, but 10 itself is not a really good number to begin with. Okay, so now we have to deal with all these base conversion and whatnot. Okay, but since we're talking about BCD and how to represent something, let's move on to how to represent non-numbers. Okay, so we're making a transition from value number representation to non-number representations. Okay, what type of non-number stuff are we talking about? Do we have to deal with non-number stuff in computer science?
Yes.
Really?
Well.
Okay, give me an example.
Well,
Strings.
charts and
Okay.
strings, yeah.
Okay, so what are those? What are we actually representing using chars and strings and arrays of chars and all kinds of stuff like that? What do we use those things for? Names, addresses. Okay. Basically stuff that do not have a numerical value, right? Okay. So we have BCD, okay? BCD, which is an IBM thing, okay? Because back in those days, IBM was pretty much the only game in town, making mainframe computers. So at some point, IBM basically have to deal with non-numerical stuff. The first computers all have to deal with only numbers and stuff like that. Well, I take it back, because the original computer at the end of World War II, what does it have to deal with? encoding text, right? So basically strings, okay, that's what it has to deal with. But in the days of IBM mainframes, okay, they look at BCD and go like, well, we can represent digits, but how do we represent letters and punctuations, special characters and stuff like that, okay? From IBM's perspective, which also made typewriters, okay, one of the things it has to deal with is how do I let a mainframe computer transmit a string of zeros and ones so that the typewriter, okay, in quotes, because it can be a printer, can print out the names, on the check, right? That seems to be a very legitimate kind of problem that IBM has to solve.
ASCII. ASCII.
No, ASCII came much later. It is called ABCDIC. Okay, so you say ABCDIC. No, ABCDIC. I think that's it. Okay. All right, so we'll look it up. ABCDIC. Yep, I got it right. It's called, you like this name, Extended Binary Coded Decimal. We certainly recognize the BCD part of it, right? Because we just talked about it. So it's Extended BCD Interchange Code. Okay, so it's based on BCD, okay, or it has some root of BCD. And this is how we encode 8-bit characters, but using BCD as a foundation, okay, as a basis. So let's see if I can find a table of this one. Yep, there you go. Here's the table of ABCDIC. And I want to zoom it in enough that we can see it. Okay, so that's kind of the table. When you look at this representation, this column deals with the values of the most significant part, and the rows deal with the least significant part. The underscore is basically the part that is represented by the column. Okay, so this 0 will go into the underscore of that 0. Will go into the underscore to the left of the 0. So if you look up this table, it's pretty easy to read actually. If you look up, and you want to find out what is less than, I put a cursor right here. So the less than symbol is represented by 003C 76. So it is a 4C. But I don't see why it's a 3C here. Okay, what is that? I think that's probably that's ASCII. But in ABCDIC, this is actually 4, okay? C. 4C is 01001100. In other words, when an IBM mainframe transmits that particular zeros and ones to a printer or to a typewriter, it will print out the less than symbol. Okay? But this table has one major flaw. Okay, let me show you where the flaw is. The flaw is this part here. Look at how A to Z are represented. A, B, C, D, E, F, G, H, I, not a problem. They're all consecutive. Where's J?
The next row.
J is on the next row, but when you look at the actual representation, I is 8. I cannot count. Okay, 8. Let's see.
Like 9.
1, 2, 3, 4, 5, 6, 7, 8, 9.
So 9. So 8, 9 in hexadecimal is representing lowercase I, but J is represented by what?
9-1.
9, 1. And there are certain values between 8, 9 and 9, 1 in hexadecimal, and they're not used.
It's all gray area.
It's grayed out, which means they're not used. So for whatever reason, IBM chose this particular table to do the conversion, and they left a lot of binary bit patterns unused. Yep.
So how do they tell the difference between a bit pattern that would be a number that would be the same or this letter? So this ones and zeros are flowing through it. It's the mainframe. How does it know this is based on what we're looking at now?
The digits have their own encoding. I think that's what you're asking. Yeah. The digits are down here. So the digits will be F0, F1, F2, all the way up to F9. Those are the digits. So if you want the printer to print out, let's say a 5, the digit 5, you will have to transmit 1111 0101. Then it's going to print a letter. It will print the digit 5 on the printer.
This is just so the printer prints it out. This is not for, oh, okay.
Yeah. Well, this is how computers communicate with each other in general. If both computers are AppSec compliant, then they will be using this table to transmit text, basically. So this is AppSec. But do we want to use AppSec? It's not easy to use. Okay. And that's why that's why AppSec was only used on IBM computers. And these days, what do we use? We use Unicode, but Unicode is based on what? ASCII. Yep. So when you look up ASCII, there are tons of entries, but Wikipedia will give you an idea of how it relates to the other type of encoding schemes. And if you run Linux on the command line, okay, you can say man ASCII. Oh, it's not installed on this one. But usually, okay, on most installations, it will give you the ASCII table as well. And in the ASCII page, you can look up AppSec. AppSec. And okay, so here we go. Until the introduction of PC-DOS in 1981, instead of ASCII, and they were oriented to punch card input and line printer output, in which the concept of carriage return is meaningless. Because their 1970s operating system used AppSec instead of ASCII, so IBM had a hard time transitioning from AppSec to ASCII, because all the mainframes are AppSec, and then the PCs, they have to be ASCII. Why do you think the PCs have to be ASCII based? Why can't IBM say everything has to be AppSec? Because I'm a giant in terms of computer stuff, so we're going to use AppSec for everything. What is the difficulty? The reason is actually on this slide, just on the same sentence of what I have highlighted already. There's one key component here that basically screams, well, we're gonna go to ASCII.
The last part, carriage return was meaningless.
No, I don't see Windows, but I do see the predecessor of Windows, PC-DOS, okay? Hold on a second here. That seems kind of self-defeating, because PC-DOS is an IBM thing, so why would IBM, defeat its own, tendency to use AppSec with the new operating system called PC-DOS? Well, that's based on a flawed assumption. The flawed assumption is IBM came up with PC-DOS. Who came up with PC-DOS? It also has a variant called MS-DOS.
Microsoft.
And that's also a flawed assumption. Who came up with MS-DOS? It's not Microsoft. Okay? You guys did not know about this? You have not read enough books on geeks, on early geeks, okay? All right, so let's take a look. Okay, I know we are digressing a little bit, but I do want to show you why we end up with the big mess that we end up with. Okay, so this is PC-DOS. It definitely has the IBM stamp on it, but it's not actually from IBM. So at the time, you can read up the stories, okay? But I'll just leave it up to you to read the stories. So here's MS-DOS. And if you read up the history of MS-DOS, it will tell you that Microsoft, Bill Gates and his gang did not actually write DOS. Okay, MS-DOS was not written by Microsoft. They contributed to the code, but they did not write the entire thing. Who wrote the core part of MS-DOS? That's the question. Okay, so let's see if I can find it real quick here. Okay. Oh, Macs were way after this. Okay, the Mac was introduced in 1984. Coincidentally, the title of a novel, and Apple capitalized on that coincidence, which may not be an actual coincidence. Okay, history. There we go. All right, MS-DOS was renamed from 86DOS, owned by Seattle Computer Products. Okay. And 86 DOS itself is also not original. It has its root. If you read really fast, you can probably track it down faster than me. Okay, it has its origin in CP/M. Okay, all the way here. So CP/M was really kind of original, okay, for microcomputers back in those days. And then 86 DOS was based on CP/M. Okay, CP/M ran on a different processor. It's called the Zilog Z80 processor, which in a way is a cousin of the early 8086 or 8088 computers, processors. So some guy looked at CP/M and go like, oh, I can rewrite this whole thing. So the guy actually rewrote, the operating system and named the rewritten operating system running on a slightly different architecture. And he called it 86 DOS. Now, 86 DOS being a CP/M clone did not really see a whole lot of sales because CP/M was the big name, and everybody just said, oh, I just want CP/M because I have a Zilog Z80 processor. Nobody paid attention to the Intel 8086 or 8088 line of processors until IBM came along and chose that as the main processor of the PCs, right? So IBM contacted Microsoft, Bill Gates and his gang, and say, we need an operating system for this architecture. How much do you think it would cost? So Microsoft gave them a number and say, okay, we can do this. Okay, and IBM said, okay, this number looks fine to me. Sign the contract. And then Microsoft later came back and say, we want to change the contract a little bit here. We want to reserve the right to sell the operating system by our own name as MS-DOS. IBM at the time thought, hey, that's okay because we are making the hardware, right? Okay, so why would anyone want to sell just the operating system when we are the one dictating and manufacturing the hardware, which later turned out to be a major flaw in reasoning, right? So MS-DOS, got the contract, and they basically said, we're not going to spend day and night writing an operating system. We'll just buy from someone real cheap, stamp our name on it, and we're done. Okay, quick turnaround time, a lot of cash. We're good for that, right? So they went to the guy who wrote CP/M, okay, because CP/M was the original, microcomputer operating system, not counting Apple II and the other, Commodore and other systems. So they went to the guy who wrote, CP/M, and with probably a suitcase filled with cash and stuff like that. Knock on the door and say, well, can we talk to da-da-da-da-da, the guy who wrote CP/M. The wife answered the door and said, well, he's golfing. That was the answer. Instead of asking, oh, who are you? Oh, you're from Microsoft and you have money and you want to buy the operating system? Let me contact him and get him back, or you can wait until he comes back. No, just said, go away, he's golfing. We're not interested. Close the door. Okay? So Microsoft then approached the guy who wrote 86 DOS, and the guy sees the opportunity. It's like, oh, they probably right here, $75,000. So Microsoft, just said, here's $75,000. We want every single right to your software. The guy said, it's yours. Give me the cash. The software is yours, along with all the rights. Okay, and that later on became MS-DOS, and Microsoft then turned around and sold it as PC-DOS to IBM. Okay, but getting back to the original point. What was the original point?
Operating system.
ASCII versus ABCDIC, right? This is why IBM has such a hard time, because the mainframes, they're all ABCDIC based because they pre-existed, right? They existed before the PCs. The PCs were using ASCII because CP/M was using ASCII. And Microsoft did not do any conversion whatsoever to make it use ABCDIC. And as a result, now you have personal computers running Lotus 123, WordStar, and whatnot using ASCII, and then you have your mainframe computers doing all the actual major crunching of numbers using ABCDIC. And that's why when IBM had to make a decision, it's like, well, what do we do with all the future computers, all the future mainframes? So at one point, they just have to bite the bullet and say, well, we'll let legacy hardware run ABCDIC. but all new operating system and all new hardware is going to be ASCII based. So that's a long history, but then it kind of helped explain why we don't even hear of ASCII anymore, because even IBM eventually has to cave in and say, well, that's not sustainable. We cannot do this anymore. So they had to change to use ASCII like everybody else. Okay, all right. Any questions? Yep.
How are we enrolled today?
Auto-enrollment, so you just have to sign into Moodle.
No password yet.
No password. Yep. I could not get it to work, or have not been able to get it to work yet. The password part.
I had a quick question.